Hello everyone, welcome to today's lecture. Today's lecture is on logic gates and circuits. So let's discuss logic gates and circuits. So the objective of our lecture is actually to define functions of 5 types of logic gates and recognize their symbols. Very important, you need to know the type of gates and also their particular symbols. In addition to that, you and me should be able to write truth tables for a given gate and recognize its gates in its truth table. We need to produce a truth table for a given logic circuit and also design a simple logic circuit to provide a solution to a particular problem. To begin with, let's understand some terms contained in our topic, logic gates. Let's begin with gates. Well, a gate is a device that performs a basic operation on any electronic device that does send some electrical signals. So logic gates are the basic circuit types and form the basis of creating an integrated circuit, the ICs. But a gate is actually a combination, or indeed gates are a combination or combined. When you combine a number of gates together, then you're going to form what is called a circuit, which will perform a more complicated task. So you have this gate, you have another gate, put together these gates will form what is called a circuit. So also look at some circuits. So these gates take in voltage. Remember, we're looking at electrical gates and circuits. So they take in some voltage on two inputs, that is in and out. So they get out specific, the gate will receive specific input or signal, electrical impulse, and they need to also give the output of a particular signal. So if it receives some electrical signal, which could be at 1, and then it can also output 1 or vice versa. So these gates are the most basic hardware mechanism used to create complex computer logic. And then by connecting these different gates together in logic designs and connecting their inputs and outputs, they get very, very powerful capabilities. Now, what is a logic gate? Well, a logic gate is an elementary building block of a digital circuit. So most logic gates have two inputs, as I earlier indicated. At any given moment, these logic gates will have a terminal that will be in either a low state or a high state. So every terminal in one of the two binary will have one of the two binary conditions. So there is going to be 0, which represents low, and high, which represents which is represented by 1, and this represents different voltage at different levels. So the state of a logic gate at a given terminal can either be low or high, and generally does change often as circuit processes data. Okay, so we'll look at logic diagrams, a graphical representation of a circuit. We'll look at a circuit. You will see familiar circuits that you could have interacted with at your secondary school in physics. Then also look at the truth tables. This will define the function of a gate by listing all possible input combinations that the gate would encounter and the corresponding output. Then also look at the circuit diagram. These again are just a representation of how electric current flows in a particular circuit. But before we look at all those things, let's begin addressing the types of logic gates that we have. So we examine these types of logic gates, the 5 of them. We'll look at a NOT gate, an AND gate, an OR gate, a NAND gate, and a NOR gate. Typically, there are several gates that one can look at, but at our level, we'll restrict ourselves to these 5 gates. So like I did indicate, we also have some truth tables. So the logic gate processes signals which represents true or false. So in this table we have when the input is 1, then the output may be 0. When it is high, it could be low. It is positive, it can be negative. Finally, we are just basically looking at on or off. You see, a circuit must be on or off. There are only two states that it will have. If you look at the switch, electrical switches in the house, when you press that button, it will switch on or it will switch off. So it will only have possible two states. So by definition, if the input value for a NOT gate, for example, is 0, then the output is 1. And if the input is 1, then the output is 0. Basically, this gate, a NOT gate, is sometimes called an inverter. Why? Because it inverts the input to the opposite. So what is the basic rule of a NOT gate? Well, a NOT gate simply states that if the input is 0, then the output is 1, or if the input is 1, then the output is 0. And this is the only gate that has one input and one output. And so that's a symbolic representation of a NOT gate. You'd see in the logic diagram, that is the symbol. That is how it is drawn. So A represents the input and X represents the output. In between that diagram is actually called a symbol. Then the truth table. Let's look at this. We have input A, then output is X. So if the voltage passing through there is low, for example, if the input is 0, it will invert, the output will be 1. And if the input is 1, then the output is 0. So it only has two possible combinations that can be done. When you look at the NOT gate, now we move from a NOT gate to a NOT circuit. How is a circuit represented? Look at that diagram. These are some of the things that you could have encountered when you were studying at secondary school. You had such things in physics. Now the same gate that we had, now this is a circuit. Look at X and A. At A, that is the input. At X, that is the output. Let's say X is a bulb and A is a switch. So then, when the switch is open, as it is there, no current flows through it. Therefore, it is at 0. So the input there is 0. But current flows through this bulb, current flows through the bulb and makes it on when the gate is at 1. So now when the gate is closed, it's at 1. More current flows and less flows through the bulb because of its high resistance. This makes the bulb to turn off. So the switch is therefore at logic 1 and the bulb is at logic 0. So when this A is connected, then the bulb turns on. When A is disconnected, the bulb will turn off. So that is a logic circuit, and this logic gate called NOT. What about the AND gate? An AND gate accepts two inputs. This is now different from the NOT gate. The NOT gate, one input, one output. AND gate, two inputs, and it will give a specific output. If the two input values of an AND gate are both 1, the output is 1. Otherwise, the output is going to be 0. So, when you are thinking of an AND gate, you need to think of it as some kind of addition, right? Not necessarily addition. It has to be some kind of multiplication rather, not addition. When you're writing the truth table, you look at A and B as input and then X as an output. So if A is 0 and B is 0, what is the output? It will be 0. If A is 0 and B is 1, what will be the output? 0. So it's like 0 times 1, you get a 0. So this output, this get will only give a positive output when both inputs are 1. So if it is receiving a signal or electrical impulse from both inputs, then the output is going to be positive as well, so it will be 1. If A is at high voltage and B is also at some high voltage, then the output is automatically going to be 1. But if any of the input is 0 or both are 0, then the output is 0. So for the output to be 1, according to the AND gate, both inputs must be 1. I want to emphasize, if the output is to be 1, both inputs must be 1. Otherwise, the output will be a 0. What about in terms of circuit, the AND circuit? Let's say input A and B are switches. Output X is a bulb. So what happens? When both switches are open, no current flows through them. Hence, they are at 0. No current flows through the bulb as well. Therefore, it is at 0 as well. So when one of the switches is closed, the bulb will still be off because the circuit is not complete. You see that? That is where, if one is 0, the other one is 1, the output will still be 0. So for the circuit to be complete, so for the bulb to turn on, both A and B must be closed, meaning both A and B will be at 1. Then the bulb will turn on. So the logic 1 here is when logic 1 closes, one circuit, one of the gates are closed, the other one is open, current will not flow. Both have to close, both have to be at 1 for this bulb to light on. I'm sure you're able to remember this concept. And now you fully understand that the kind of concept you're looking at here is an AND gate and AND circuit. So we are considering simultaneously, we look at a gate and we look at its a logic circuit. So it's a logic gate and also it's a logic circuit. Before we discuss quite a lot, let's look at the concluding logic gate and circuit for today. We'll look at the OR gate. If the two input values are both 0 according to the OR gate, then the output value is also 0. Otherwise, the output is 1. So it's the opposite of the AND gate. OR meaning, you see, when you say either Mlenga or Chanda will come, so do you expect both to come? No. But should any one of them come, then you have a representation. Otherwise, there will be no representation. So here we have a truth table, and that is a logic symbol. By the way, I hope you had paid attention to the logic symbol for the AND gate. It has that symbol. That's how it is drawn. So that is an AND gate. AND gate, please. And then this is for an OR gate. So if the input is 0, input A and B are 0, then everything comes to 0. But if input A is 0 and input A is 1, input A is 0, input B is 1, then the output is going to be 1. At least one of the input will be 1, then the output will be 1. Otherwise, it will be 0. So the consideration is that at least one input in the OR gate should be 1, then the output will be 1. If both inputs are 0, then everything is actually going to be 0. Let's look at its circuit. So you look at A and B, we are taking those as to be switches and X as a bulb as usual. So when one of the input A or B is closed, what do you think would happen? The current will still flow through the bulb and it will be on. If you close A, you see that there's going to be some flow of current and A will be, the bulb will be on. And if But when both are open, when both are at 0, the bulb will not turn on. So for the bulb to turn on, one of the gates must be closed, meaning one of the input must be 1, then the output is going to be 1. So that's what I thought we can share today on logic gates and circuits. So the next time I'll talk to you, we'll look at the NAND gate, and then we'll conclude with the NOR gate. So I'll send you these notes so that you can briefly look at them and see the application that you note from these gates. So for today we've ended on the OR gate, and once again we've just looked at 3 gates. We've looked at the NOT gate, AND gate, and the NOR gate. So you take note of the symbolic representation of these gates and also the truth tables, and not forgetting the circuit diagrams of these gates. These are very, very important. So you have these notes, you can play back at your own time, you can pause to study the diagram carefully and also to study the logic circuits carefully. So I want to appreciate you for taking your time to download this video and also listen to this presentation. We'll see you again. Thanks.